Swayam Prabha. Digital India. Educated India.
So today we will resume where we stopped last time, that is the voltage transformers. We will just briefly go over what we started last time, and then we will continue with some new concepts. So as we said last time, a voltage transformer is unlike a current transformer, which we said was a current source driven device. Here this is very similar to a power transformer, and the theory is also very similar. The equivalent circuit of course is very similar, as you can see on the screen, is the same as that of a conventional power transformer or a conventional transformer. Let us not distinguish between power transformers and distribution transformers. This is the same. However, there is a difference, and as you can imagine, the secondaries of voltage transformers or VTs, also known as potential transformers or PTs, is standardized to 110 volts. If you remember, for current transformers we had standardized the secondaries to either 5 amperes or 1 ampere. This is so that the relay inputs can be standardized, relay or meter inputs can be standardized to those numbers. Otherwise, you could have a wide variety. Similar is the case with voltage transformers. Here it is standardized to 110 volts. So if your primary is 11 kV, then the PT or the VT will be rated for 11 kV by 110. As you go up higher in voltages to transmission levels, this can become 33 kV, 66 kV, 132 kV, 400 kV, or even higher. Now you can imagine that if you are primary transmission voltage or the primary voltage on the voltage transformer side is 400 kV and the secondary has to be 110 volts, the turns ratio will be 400 by root 3 is to 110 by 400 kV by root 3 is to 110 volts by root 3. So that's a massive number. So the transformer itself would become very bulky and difficult to handle and all that. So what we do is we use a voltage divider. Now unlike a conventional voltage divider, we use a capacitive voltage divider for reasons of cost and economy. So here what we do is this is how the voltage divider will look like. Okay. So we have this is of course not single capacitors, they are a bank of capacitors, both C1 and C2 can be banks of capacitors, and then we have a conventional voltage transformer here, this one, which is usually of the ratio 11 kV is to 110 volts. So this is standardized, and the secondary voltage is of course 110 by root 3 or 110 line to line. Okay. So and the ratio here will be C1 upon C1 plus C2 is equal to Vc2 upon Vc1 plus Vc2. Okay. So we get Vc2 as 11 kV, and then which is further stepped down to 110 volts and which can be read by the meter or can be used as the input to the relay. Now if we analyze the equivalent circuit, then we will have to start with the Thevenin equivalent. We will do that shortly. In fact, we can it's quite simple to analyze because we have made a few assumptions here. C2. Okay. This can be the leakage reactance of the conventional or the electromagnetic PT that we are using here. I am making the distinction as electromagnetic PT just to distinguish with the capacitive voltage transformer or CVT that we are talking about. Okay. A is to 1, this is ZB. Okay. Now, we can this is assumed to be whatever is the leakage impedance is assumed to be L, and we can get this ZB to the primary side, that is for ease of analysis. And then if we find the Thevenin equivalent, how do we start with the Thevenin equivalent? This is the primary voltage here, this you can call this Vp, and you have to short this, and then the open circuit Thevenin voltage can be at that point can be thought of as ETH. Okay. And if this is taken as an ideal transformer here, then we ignore the L. And we will get simply A square ZB, and this is 1 upon omega C1 plus C2. Okay. Now, as you will notice that because of this capacitance, there will be a shift in the phase. Okay. And name it as VTH, and then if this is VTH, then this will be VC, and then there will be a shift in the phase and as well as the magnitude of VTH, which is not what you desire, because then there will be an error in your relaying or your metering or whatever that you connect to the secondary of that transformer. So, to compensate for that, what do? You add a inductor which is known as a tuning, because it cancels the capacitive effect, then it is known as the tuning inductor. Okay. So, that is this value here. Now, this could be externally added inductor, or you could design the this transformer here, this voltage transformer here, such that this its leakage impedance matches the L that you require from this circuit. Okay. So, we will have a look at the slides now. Okay. So, this is what we discussed. A tuning inductor is inserted or connected to compensate for the capacitance effect. Okay. And the value of the inductor is adjusted such that omega L is equal to 1 upon omega C1 plus C2. Omega is of course the supply frequency, which in our case is 50 hertz. So, this is the on the top right hand corner you can see the phasor. So, you will it will compensate for the capacitive effect here. Okay. This is the equivalent final equivalent circuit of the CVT or the CCVT. Okay. So, why it is called a CCVT we will come to very shortly. Okay. CCVT means coupling capacitor voltage transformer. Earlier we referred to it only as CVT, which is capacitor or capacitive voltage transformer. Why that coupling word has come in, we will see it very shortly. Okay. CCVT means coupling capacitor voltage transformer, and this is used in power line carrier communication. Nowadays of course, we extensively use fiber optic communication. There is a fiber optic cable which is embedded with the earth wire, if it is a, a single earth wire, or if there are two earth wires, then at least one of them will have a fiber optic communication. The necessity for this is that the power utilities realize that they need to have control over the communication circuits. If their sensitive protection or even other control information has to be communicated to other substations or other control areas. So it did not make it was not considered good practice to rely on external communication circuits. So you already had wires. They may be the phase conductor or even the earth conductor already going from substation to substation. So that is why we could use this for communicating signals. Now, for this specific application of the CCVT is used in power line carrier communication. Now, as the name suggests, it uses the power line conductor, the phase conductors for communication. Now, it can be phase to ground or phase to phase, it can be analog or digital. It is still used mostly digital PLCC. PLCC is power line carrier communication. It is still used, but in the digital format. Now, here the a carrier signal is introduced along with the normal 50 hertz signal, and then it is modulated and tapped at the other end, and the information is extracted. It could use frequency shift keying also, depending on type of the communication that you are wanting. We are not discussing the PLCC per se, so we will not go into too much of detail here, but we will just look at the how the CVT is modified and becomes a CCVT for the purpose of PLCC or power line carrier communication. So here the signals are of high frequency, could be in the range of 40 kilohertz to 400 kilohertz or even 500 kilohertz. That depends on the country and the specific licenses, etc. But it is in that range, around 50 to 500 kilohertz. And as you can see on the slide here, the CVT is modified slightly. What you can see here is that there is a reactor connected. Before that, at very high frequencies, that is the range in which we are talking of kilohertz, hundreds of kilohertz for the power line signals, the capacitor of the capacitive voltage transformer presents a very low impedance. So the communication signal will be routed through that path, and then you can extract it using a tuning pack, which is a RLC combination. So that is one path for the communication signal. To avoid it going to the ground, there is a inductor placed at the, we will show it here, at the ground side of the CVT here. Okay, this is your CVT. This is what we have seen till now. I have not drawn the complete thing. Of course, there will be an inductor here also. This is your tuning inductor. We are talking specifically of this inductor here. This is known as a drainage inductor. Now, we said that these capacitors provide a low impedance path for the communication signal. Here, of course, is your tuning pack, which is an RLC, parallel RLC circuit. This is used to extract the communication signal, but to avoid it shorting to the ground or draining to the ground, we use a drainage inductor. Now, this at power frequency provides a very low impedance. However, at the high hundreds of kilohertz frequency, this will provide a very high impedance and blocks the communication signal from draining to the ground. That is why it is known as a drainage inductor. Similarly, on this side, there will be a blocking inductor, which will block the communication signal from going on the further on the line. So, this is known as a wave trap. Okay. This is present in substations. If you see, it's an air cored inductor, like a Diwali lantern. It will be present at the entrance of the substation. So, on both sides, on this side there will be a drainage inductor, and on this side there will be a wave trap. Of course, we are not studying the PLCC in detail, so we are not going to further into details of these devices. Okay. So, that is the communications devices that are there. Now, coming back to our CCVT or CVT or CCVT, as now we have mentioned it as CCVT. We also have something known as a ferroresonance suppression circuit. Now, we will not go into the phenomenon of ferroresonance in great detail, but we will just mention it shortly because it is of importance and it can cause failures of CVTs if not handled properly, or if the ferroresonance circuit is not present. Okay. So, ferroresonance is associated with, we will just briefly write it down. Is associated with a series RLC circuit where L is non-linear and R is generally negligible. R or the damping is generally negligible. Okay. This in the ferroresonance in the series resonance phenomena, what happens is the capacitive impedance matches the inductive impedance. Similar thing happens in ferroresonance. Of course, calling it as a series resonant phenomenon is a bit simplistic, because in a series resonant phenomenon the waveforms will still be sinusoidal, but in a ferroresonance phenomena that in our case also our equivalent circuit with a low burden would look something like this. Neglecting the burden here. So, this is 1 upon j omega C1 plus C2, and this is j omega L, and if this is of course a nonlinear inductor, and if we draw it on the V versus I diagram, let us see how it looks like. The nonlinear inductor can be represented by a curve which is very similar to the BH curve. The reason for that we have seen when we saw the CTs, and if the this is the V versus I for the L, and if the capacitance value is low, then you will have an intersection somewhere in the linear part, and there will be only one intersection point. However, as the capacitance goes on increasing, this line, the slope of this line will keep on changing, and you could have a condition like this, okay, where there is an intersection at multiple points. Okay. And then what could happen is, if there is a slight change in the circuit parameters, there could be a constant oscillation between these operating points. So, this leads to the phenomenon of, or this is what is the phenomenon of ferroresonance. Now, we said that in a series resonant circuit, the waveforms are still sinusoidal. However, in a ferroresonant circuit or in a circuit where there is ferroresonance, you will find the current waveforms especially will be of a peaky nature like this. So there will be a very high peak. The RMS value of course will be much lower, but you will get a very high peaky waveform, and the voltage waveform will also be non-sinusoidal. It will be something of this nature. So this is V, this is T, and you will have, let me just take it a bit. And so on. Okay. So this, as you can see, is not a sinusoidal waveform, and it can lead to failure of VTs also, and in fact it does lead to failure of VTs. Quite a lot of time we find that in the field, if the ferroresonance circuit is not designed properly, then you will have a problem of ferroresonance and over voltages due to ferroresonance, and the CT, the PT or the VT gets completely destroyed. So to avoid that, we have a ferroresonance circuit also present, which is also a combination of L and C to change this resonant frequency. Okay, so that covers the basic part of the CVT or the CCVT. Now the problem is, after we add the ferroresonance circuit, there could be an issue with the transients or the settling transients or the subsidence transients with the CVT. Now that is because you have now a series RLC circuit, and as you can see, this is the differential equation: dV by dt is equal to R di by dt plus 1 upon C into I plus L square d2I by dt2. Now you are well aware that the solution to the circuit or the response will be oscillatory in nature. That depends on the damping and also the oscillatory frequency, which is 1 upon root LC. Okay, omega square is equal to LC, and the damping is of course depending on the R. So 2 zeta omega n is equal to R by L. So this is the standard form of the equation. So the response of the circuit will depend on the damping constant, the natural frequency, and of course the point on wave at which the switching phenomena, could be a fault or could be a switching phenomena, strikes. So these are known as subsistence transients or the settling transient of the CVT. We will see a resulting waveform. You can see that there is a change in voltage due to the fault, but however the CVT does not immediately latch on. Okay, there is a oscillatory response before it latches on and tracks the primary voltage correctly. Now that is because of the ferroresonance suppression circuits that are present. So here you can see that go to the earlier slide. Here we can see that the peak has overshoot. There is a peak overshoot here present in the response. Now this will cause a problem in your relaying decisions, okay, because it could read a higher voltage than necessary. I mean, it could be a distance relay may not operate because after all it sees Z apparent, which is equal to V by I, and if the V is high, then the Z apparent could also lie outside the region in which you are choosing to trip. So you can observe this incidentally at there is a with capacitances you will get this sort of lag effect. If you take your laptop and switch it off, or you switch the power off, you will still see that the power LED still glows. So that is because of the capacitances in the circuit. So a capacitor will in layman's terms will tend to remember the voltage. So that is why this phenomenon will result. And so this is another example of of a CVT transient. Here you can see that the overshoot is much lower. That is because the the point at which the fault strikes here is different. Okay. So now we move to classes of CVTs. Like we saw the class of CTs. Here also, they are depending on the error. There are the CVTs or the CCVTs are also classified into two types, class 1 and class 2. We will see what the class 1 implies. Class 1 CVT or CCVT is the maximum ratio error is plus minus 1%, and the phase angle error is plus minus 40 minutes. Okay. Similarly, for a class 2 CVT, the maximum ratio error is plus minus 2%, and the phase angle error, maximum allowable phase angle error is plus minus 80 minutes. So, to conclude the topic on CVTs or VTs, we have seen what is the role of the voltage transformers. We require it for relays like distance relays and some other relays like frequency relays, etc. We saw the equivalent circuit of a CVT or a CCVT. We saw how it is used in PLCCs or pilot wire communication. Then we very briefly saw the ferroresonance problem, and then classes of CVTs. Before we end this, we will solve a problem. This is a slightly longish problem, but it will give you an idea of CVTs in general. So, we will solve that before we go on to the next topic of symmetrical components. Now, if this, if our discussion leads you to the conclusion that only CVTs are used in power systems, that is not the case. There are some applications even with very high voltages or extra high voltages that conventional VTs, by conventional I mean no capacitive voltage divider, a direct ion code VT with the ratio of say just for an example 400 kV by 110 volt. These are used. There will be of course one more stage there where there will be an 11 kV PT also, but electromagnetic PTs as they are known as, because they to differentiate them from CVTs, they are also used specifically in applications like gas insulated substations, etc., where the capacitors, gas insulated capacitor themselves are very expensive. So the electromagnetic VTs become more economical. So in those applications they are used. So both can be used depending on the application that we are looking at. Okay. So we will solve one problem in the tutorial. Maybe the next one we will solve, so that we get an idea of a better idea of CVTs before we move on to the next topic, which is symmetrical components. Okay. So the problem is the equivalent circuit of a CCVT is shown in the figure. This is similar to what we have been looking at so far, and here what is the problem that has to be solved? We will just okay. The values of C1 and C2 are 0.0018 microfarad and 0.00186 microfarads respectively. The tuning inductor has an inductance of 497 henries and a resistance of 4620 ohms, 4.6 mega ohms. Now these values are a bit high, but for a problem we can live with them. Otherwise 497 is a very huge inductor. Maybe we need to modify the values, but let's stick with them and let's just focus on the problem at hand. XM of the VT referred to the 6.6 kV side is 1 mega ohm. Core loss is 20 watts per phase. The VA burden is 150 volt amperes per phase. Value of CM for the compensating the current drawn by XM is equal to 3.183 narofarads or 3.183 into 10 raised to minus 9 farads. Okay, so what do we have to do? Verify the appropriateness of the choice of L and Cm. Find out the nominal value of V by V2 or V1 by V2, and if the frequency drops from or changes by 3 hertz or reduces by 3 hertz from 50 hertz to 47 hertz, what would be the values of the ratio error and the phase angle error. Okay, so we will solve this, and okay, we will draw the diagram because it is easier to refer to. This is Xm, and this is a capacitor which is designed to compensate for the Xm, and the burden is given as 150 V. This V2 is mentioned as 6.6 kV, and the line voltage is V. I mean, the primary voltage rather should be V. It is the voltage to ground. Okay. So now to find L, what we need to do is in fact we can do this the other way. Just okay. So here or 2 pi f naught is equal to 100 pi, because we are talking of a 50 hertz. F naught is 50 hertz. Okay. Okay. This actually L is okay. This C is C1 plus C2. Okay. So now L, if you just substitute, C1 is 0.0018 and C2 is 0.186. So if you just substitute here, what will we get? 100 pi square into so these are in microfarads. So you multiply by 10 raised to minus 6. So if you do all this calculation, you will get a value of 496.7 Henry, which is what we started off in the first place. So our L was given as tuning inductor H. So this matches, so that the choice of L is appropriate. That is what was asked in the first part of the question. So L has an appropriate value, you can say. Of course, as we said, 497 Henry is a very high value of inductor, but for the sake of this problem, let's not look at that in so much of a minute detail. Now, the second part is calculating Cm. Okay. So, the CM is designed to compensate XM, okay, which is the magnetizing reactance. Okay. So, the XM is referred to as XM referred to the 6.6 kV side is given as 1 mega. Okay. So, because we have said that Cm compensates the Xm. So, we get Xm equal to 1 upon omega naught Cm. So, Cm is 1 upon omega naught or omega naught here is 2 pi. This here could also be referred, we could change this to omega naught, just change it for consistency in our notations. So, this will be equal to this is because it is 1 mega ohm. Okay. So, if you solve this, you will get 3.183 into 10 raised to 9 farads. So, the choice of Cm is also appropriate. Okay. So, what is the second part? The second part is find nominal value of line voltage. That is, we want to find the value of V, this V. Okay. We know the value of V2 is 6.6 kV. Now, we need to find the value of V. Okay. So, from the capacitor voltage divider, we know that V2 by V is equal to C1 upon C1 plus C2. So, this is 0.0018 upon 0.0018 plus 0.0186. Okay. So, this if you solve, you will get 1 upon this ratio is 11.33. Just write it again. Okay. So, V is equal to 11.33 into 6.6 kV is equal to 132 by root 3 kV. Okay. So, the primary line voltage nominal value is 132 kV, 132 kilovolts. Okay. So, this is how you proceed. Okay. So, we will look at the third part, which is a slightly detailed calculation, but we will have a look at it anyway, so that we complete this topic. So, what was the third issue? So, the frequency has dropped from 50 hertz to 47 hertz. Okay. So, we want to find out the ratio error and phase angle error. In other words, we want to see what happens if the frequency changes. Will the if it was a class 2 CT with plus minus 2% ratio error and plus minus 80 minutes, will the performance remain the same, or because the frequency has changed, will the performance of the CT change to some new value? Sorry, will the performance of the VT change to some new value? So, how do we start this? We have been given a core loss value of, let me see, it is 20 watts. Okay. So, we have, what is the secondary voltage there? It is V is equal to, or V2 is equal to 6.6 kV. Okay. So, we are finding the magnetizing impedance here, or the magnetizing resistance here from the core loss value. So, we have V square by Rm is equal to 20 watts. Now, V square B, as we know, is 6.6 kV or 6600 volts. So, 6600 square by 20 is equal to Rm. Okay. So, Rm, if we calculate that, Rm is equal to 2.18 into 10 raised to 6 ohms, is 2.18 mega ohms, okay, which seems an okay value here. Okay. So, also we have been given the VA rating or the VA burden here, not the rating, the VA burden on the CVT is given as 150 volt amperes. Okay. Let us make a simplifying assumption here that this is a resistive burden. Okay. Or it is resistive in nature, so that it just simplifies our calculations or makes our life a little bit simpler. Okay. So, we have been given similar to that power calculations that we did earlier for a voltage rating of 6.6 kV or 6600 volts and a power rating of 150 VA, what would be the resistance rating? So, we will designate the burden resistance as R dash B, that is because it is referred here on this side, and that will give us R dash B is equal to 6600 square upon 150. If we do this calculation, please do it yourself and see and verify rather. You will get 2.904 into 10 raised to 5 ohms or mega ohms. Okay. Now, we will draw the equivalent circuit and have a look and solve it further. Okay. We will have to simplify the equivalent circuit a bit. Okay. So, this is 6.6 kV or 6.6 into 10 raised to 6 volts. Okay. The equivalent capacitance here is C1 plus C2, which is microfarads. The L we have been given as 497 or 496.7 Henries. Let us take 497 for convenience. This Lm is okay. Then we have an Rm which we calculated. Then also we have a same, we will write those values shortly. And the burden impedance, burden resistance rather. So, this is R dash B is 2.904 into 10 raised to 5. this is Rm, which is, what was it, 2.18 into 10 raised to 6. This is ohms. I am skipping that because, okay, we'll write it as ohms. Okay, and this C is 3.183 into 10 raised to 9 farads. Okay, let's check the Cm. 3.183 into 10 raised to minus 9, I'm sorry, not 9, 9 is a minus 9 farads. Okay, we have also been told that Xm is equal to 1 or 1 mega ohm at 50 hertz. So we have okay. We'll just verify this. Lm is 10 raised to 6. Okay, so we will now they can simplify this as an equivalent RLC circuit, series RLC circuit, where the appropriate this is, of course, you can write it as V or VTH as equal to 6.6 kV. Then you have a C equivalent, then an R and a L. This voltage we can call it as the secondary voltage or the transformer voltage. Now the thing to note is that earlier we calculated the values at 50 hertz. Now the frequency itself has changed to 47 hertz. Okay, so we need to recalculate the values. So for the series circuit, and we need to add the burden resistance also. So 1 upon the Z will, or rather 1 upon Z will give us the values of the R's will not change. So this is 2.8 mega ohms, and the value of X and C of course will change. So this is 2 pi into, instead of 50 now we have 47 into 3183 henries, plus we have omega Cm. So we will have 2 pi into 47 into 3.183 into 10 raised to minus 9. This is the for the C, and one for the burden resistance also. So we have, that will not change because it's a resistance, into 10 raised to 5 with the appropriate units. Okay, so this if we solve, we will get, please solve it for yourself and see that the values that I have calculated are correct. Into 10 raised to minus 6. Okay, if you write it this in the polar form, you will get degrees. Okay, so z will be 1 upon this. This was 1 upon z, of course. So z 1 upon this will be 3.904 into 10 raised to minus 6, and angle, of course, we can write directly as 1.82 degrees. So this will give us this is as I have said before also, please do this calculation for yourself. It is possible that I may have missed some or made some error in some digits here or there. Please verify for yourself. Okay, so 2, 5, writing it in the rectangular coordinates, we will get plus j ohms. Okay. Now, from the circuit, we have the current flowing in the circuit I Thevenin sorry, V Thevenin upon R plus j omega L minus plus 1 upon j omega C plus z. Okay. Okay. Now, since with VTH or this here, this voltage here across the burden is given by, or VT is given by I Thevenin into Z so VT is equal to, let us assume that the phase angle of the source is 0. So please substitute the values and you will get this. What was it earlier? 256147.5, 6147.5, angle 1.82 degrees. Okay. So the voltage that is obtained across the burden, it may be connected to a relay or a meter, is volts. Okay. Now, what is the amplitude error? Amplitude error is simply VTH minus VT upon VTH into 100% is the amplitude error. I am sorry, or the ratio error you can call it. So this is into 100%. So ratio error, I'm sorry, this is you can call it amplitude error or ratio error. So since we have earlier referred to it as ratio error, we will stick to ratio error is equal to, if you calculate these numbers, it will give you 1.81%, which is okay if it was a 2 class 2 CT. However, you have to note that the phase angle of the source was 0 degrees, that is VTH was 0 degrees, and VT or the angle or the voltage across the burden, the phase angle of that is 4.26 degrees. Okay, so the phase angle error is 4.26 degrees, which is very high. Okay, so this may not be acceptable. Okay, so that completes our problem, and we will stop